2025 A-Level Combined Mathematics Paper 2 Part B, question number 12, Part B. Part A of the same question we discussed in a previous video, link in the top right. Part B says, a smooth, thin, rigid wire AB in the shape of a circular arc of radius A, center O, and angle AOB equal 2 pi by 3 radians is fixed in a vertical plane with OA vertical as shown in the figure. So in the figure we can see it is like this. A smooth small bead of mass m is kept at A and projected along the wire with a speed of root 7GA over 2. Given this, we are asked to show that the speed v of the bead when it has turned through an angle theta, which is somewhere in between 0 and 2 pi by 3 radians, 2 pi by 3 radian inclusive, about O is given by v squared is equal to GA over 2 times 3 plus 4 cosine theta. We are then asked to also show that after leaving the wire, the bead comes back to A and find the speed of the bead when it reaches A. So basically what they're saying here is that this particle is going to go along the wire, it's going to reach the point B, and then after that it's going to go out of the wire at the point B projected upward like this. It's going to follow a path that looks something like this. It's going to go back down, and as it goes down, it's going to pass through the point A and keep going. So when it passes through the point A, what we are asked to do is to find its velocity at that point. So basically we need to use the gravity and the motion and everything that we know at that point in order to find the velocity of the particle as it travels through this point, and of course before that we need to prove that it travels to this point. So to start off this question, we need to show that v squared is equal to GA over 2 times 3 plus 4 cosine theta when the particle turns through an angle theta like this from the downward vertical all the way up to current position. So given this, what we're going to do is to apply conservation of energy. The reason we can apply conservation of energy in this situation is because we are not losing any energy to friction or anything else. If we were losing energy to friction somewhere, then we wouldn't be able to do this. But in this particular case, the bead and the rigid wire here and everything is frictionless and smooth, and there's no energy loss anywhere, so we can apply conservation of energy. So here what I'm going to do is to call the level at A, where A is the starting point, PE equals 0. So basically we're measuring potential energy from this point relative to this point, meaning that this point is our 0 point, so PE equals 0. So at this point, when the bead starts its motion, it has a velocity in this direction, the tangential direction, of root 7GA over 2. So it's traveling like this, and as it travels along, it's going to slowly go up and up the wire. As it goes, it's going to have turn to an angle theta, let's say. At that point, let's suppose it has a velocity of v, and it is a certain height above the PE equals 0 value. So at this point, its potential energy plus kinetic energy is still going to be equal to the initial potential energy plus kinetic energy of the bead. So due to that, we can say by conservation of energy, the initial PE energy, which I'm going to say potential energy initial, plus the initial kinetic energy, which I'm going to say KE initial, is equal to the final potential plus kinetic energy, which I'm going to write as PE final, plus kinetic energy final, which I'm going to write as KE final. So now, if we go around substituting for this, the initial point is this point here where we're at A. At A, PE is defined to be 0. Well, I defined it to be 0. So therefore, at that point, let's say that PE initial is equal to 0. And then plus KE initial. KE initial is going to be half mv squared, which in this case is going to be half times the mass m times v squared, which is going to be root 7GA over 2 whole thing squared. So we can write root 7GA over 2 whole thing squared. We could have just removed the square root immediately, but I prefer writing it like this because it's more clear. Now, as for the PE final and KE final, PE final comes from the height that is gained by this particle. Now, considering the height that is gained, we can find it based on this triangle right here. Considering the total height of the point O from the point A, that height is A right here, which is the total height, the radius of our circular path, and out of that height, this height right here is A cosine theta. So the height that's left over, this height, the height from P equals 0 up to the point, is going to be the whole total height A minus A cosine theta. Now if you're wondering what happens when we get up here when it's actually greater, what's actually going to happen is that the cosine of the angle is going to be negative when the angle is greater than 90 degrees. And due to that, when we subtract, we're actually getting a value greater than A. So when we do A minus A cosine theta for an angle theta that is greater than 90 degrees, we're actually getting the proper height, which is a little bit higher than the actual radius A. So due to that, what we have for PE final is going to be mgh, where h is going to be A minus A cosine theta. So we have mg, and I'm going to factor out the A to write A times 1 minus cosine theta. And then KE final is going to be half m, and the velocity is v, so we have half mv squared. Now what we're going to do is to take this, simplify it down, and eventually get that v squared is equal to the expression that we had above. So simplifying down on the left hand side, if we do something like this and take it down here, we're going to have half m times 7 ga over 2 equal to, and on the other side we're going to have mga 1 minus cosine theta plus half mv squared, which we can see we can divide out the m, and additionally we could also multiply everything by 2 to get rid of the halves. So if we do that, we're going to have 7ga over 2 equal to, here if we multiply everything by 2, we're going to have 2. When m is gone, we're going to have ga 1 minus cosine theta plus v squared. Now all we want is v squared, so we can take the other things to the other side and write that v squared is equal to, and what we have is a ga factor which we can take out. We can actually take out a ga over 2 factor. Doing so, we get ga over 2, and what we're left with is 7 and 2 times 2, which is going to be 4, so plus 4 times, and then the 1 minus cosine theta taken to the other side is going to become cosine theta minus 1, so we have 4 times cosine theta minus 1. Now if we simplify this down, we can see we get v squared equal to ga over 2 times, we have 4 times plus 3, plus 4 times negative 1 is going to become minus 4, 7 minus 4 is going to become 3, so we have 3, and then 4 times cosine theta is going to be 4 cos theta, so we have 4 cosine theta, and that is the formula that we wanted. So we've shown that v squared is equal to ga over 2 times 3 plus 4 cosine theta, and all we need to do is to realize that since there is no loss of energy here, we could actually apply the conservation of energy in this situation. So now we've proven that v squared is equal to ga over 2 times 3 plus 4 times cosine of theta, but we also need to say this is 4 thetas in between 0 and 2 pi by 3 radians. And the reason for this is that when we get to theta equals 2 pi by 3, after that point we're no longer going to be on this circular path, and due to that this equation no longer holds. So for that reason we'll say it only works for theta in between 0 and 2 pi by 3 radians. So now after that it says also show that after leaving the wire, the bead comes back to A and find the speed of the bead when it reaches A. So for this, what we need to do is to find the final velocity of the bead as it goes out of this circular wire here, and when it goes out, we then need to calculate its path of travel, and after doing that we can see whether it passes through the point A and then what the velocity of it is as it passes through A. So for this I'm going to say that the particle leaves the circular wire at theta equals 2 pi by 3, since that's the last angle that we can have and still be on the circular wire, since after that point when this angle becomes 2 pi by 3, then we're going to leave the wire. So if I mark that down, the angle is 2 pi by 3, meaning after that point the bead is no longer going to be on the wire. So at this point, if it leaves at that point, then the velocity, let's say v, as the particle leaves the wire is given by, and then we can substitute into v squared is equal to ga over 2 times 3 plus 4 cosine theta, the angle 2 pi by 3. Substituting in 2 pi by 3. So when this happens, we have ga over 2 times 3 plus 4 times the cosine of 2 pi by 3, which is going to be the cosine of the negative cosine of pi by 3, which is going to be negative 1/2. So we have negative 1/2 here. Now if we simplify this down, we have GA over 2 times 3 plus 4 times negative half is going to be minus 2, which is going to be GA over 2 times 1, which is going to be GA over 2. So therefore V squared is going to be equal to GA over 2 as this particle leaves. Now as it leaves, if we consider the situation, we can see at this point when it leaves, it's going to leave like this at this angle, and if we consider the angle involved, this angle right here is going to be 2 pi by 3 minus 90, which is going to be pi by 6. So this angle is pi by 6, meaning that if we consider the rest of the angles, the angle over here is going to be pi by 6, meaning that the remaining angle here is going to be pi by 3. So it's going to travel at pi by 3 like this. So the angle between the horizontal and this particle's motion is going to be pi by 3. So we can use that to try to figure out the motion of the particle. So if we go down and draw this, if we go down and draw the projection that's happening at the point B, the particle is going to be traveling like this at a velocity of root GA over 2 at an angle of pi by 3, and the point here is B. Now we could of course also draw the rest of it, and I'm actually going to do that. I'm going to draw a little bit of the rest of it. The point A is somewhere down here, the point O is somewhere in the middle, like over here, let's say, and it is moving like this. Now what we want to show is that if the particle travels under a projectile motion like this, it is eventually going to reach A again. To do this, what we're going to do is to apply S equals ut plus half at squared for the motion of this particle under gravity, and then by doing that we're going to see if it does in fact reach A. Now to do that, what we're going to do is to see if the horizontal and vertical displacements are both going to get us to point A. So if we consider the horizontal and vertical displacements from B to A, AB in the horizontal direction, horizontal component of AB, actually we could say like horizontal distance from A to B is equal to, and if we consider the horizontal distance is going to be this distance right here, and that distance can be found based on this angle, which is pi by 6. If this is A, this is going to be pi by 6, cosine of pi by 6 times A, which is going to be A times root 3 over 2, so it's going to be root 3 over 2A, root 3 over 2A, and as for the vertical distance, we can also write the vertical distance from A to B is equal to, and that vertical distance is this distance, which is A sine pi by 6, which is going to be A over 2, plus this distance, which is A, so it's going to be A over 2 plus A, which is going to be 3A over 2. So these are the two distances that we need. Now if the particle at point B from point B horizontally travels a distance of root 3 over 2A and vertically travels a distance of 3A over 2, then it's definitely going to be at the point A. So what we need to do is to show that if the particle travels horizontally this distance, it is going to travel vertically this distance. So what we're going to do is apply S equals ut plus half at squared. So in this particular situation, applying it, let's say horizontally in this direction, we're going to assume that it travels the distance that we want, which is going to be root 3 over 2A is going to be equal to ut plus half at squared. Now ut, in this case u is going to be this velocity times the cosine of pi by 3. So it's going to be half root GA over 2 times the time, which we don't know, which I'm going to call t, plus half at squared. Now half at squared is going to be equal to half, and in this direction, horizontal direction, we have 0 acceleration, so it's going to be half times 0 times t squared, which we can actually cancel, but we'll leave it for now. So from this we can see if we rearrange, t is going to be equal to, rearranging this thing, we have root 3 over 2a times 2 root 2 over GA, which if we simplify we can see we have root of 2 and root of 3, which is going to be root of 6. This 2 and this 2 can cancel, and when they cancel we have a here and root of a on the bottom, which means we have root of a on top. So we are going to have root 6a over g. So therefore the time taken for this is going to be root 6a over g. Now for this, if we apply in the vertical direction, the height, which I'm going to call h for now, is equal to, and actually we should consider it down, because if we consider it downward, then we'll get a positive value. So if you consider the velocity down, the distance downward, it's going to be h, which is going to be ut. In this case, since u is upward, we're going to actually have a negative value. We're going to have negative, and u is going to be root ga over 2 times the sine of pi by 3, which is going to be root ga over 2 times root 3 over 2 times the same time, which is going to be t, which I'm going to direct to, actually we'll leave it for now. We'll substitute on the next line. And then plus half at squared, which is going to be plus half g t squared. Now substituting in the values, we get h equals negative root ga over 2 times root 3 over 2 times t, which is root of 6a over g, and then plus half g t squared, which is going to be half times 6a over g. These cancel for this, and 6a times half is going to become 3a, and on the other side we have root of g on the bottom, root of g on top, which cancel, and we're going to be left with minus root of a times root of a is going to give us a, then root of 3 times root of 6, one of this is going to cancel and give us, actually we can do this first, this 2 on the bottom and this can cancel to give us 3a here, and then the 3a times root 3 times root 3 is going to give us 3a, divide by 2 means we have negative 3a over 2, and then this thing is going to give us positive 3a, which if you add together is going to give us 3a over 2, positive 3a over 2, and that is the exact same value that we expect in the vertical distance from A to B. So we can see, therefore, since the vertical distance was achieved when we assume the particle, the bead, traveled the horizontal distance required, we can see that therefore the particle, the bead I should say, bead reaches the point A after leaving the circular path at B. So we've proven that part. Now for the final part of the question, it asked us to find the velocity of the bead as it passes the point A. Now we can easily find this is not that much to talk about, but I'll just write a single sentence to answer it. We can say, by conservation of energy, since the particle didn't lose any energy along its entire journey and it returned to the same exact level at the same exact point A, the same exact kinetic energy and potential energy should be there in that particle before and after all of this motion. So by that we can say, by conservation of energy, the speed of the particle is equal to root 7ga over 2. And the reason I can directly say this is because by conservation of energy, along its entire path from the start, at the start it had half m times root 7ga over 2 squared energy, and at the end of its motion, when it passes the point A again, it's going to be at the same level, meaning that the kinetic energy is going to have the same exact value, meaning if you divide out, you're still going to get v squared is equal to 7ga over 2, meaning that root of that is going to give us that velocity v is going to be root 7ga over 2. Now of course the direction has changed, but the actual value of the velocity itself, or the speed that we're interested in, is going to be the exact same, root 7ga over 2. So that is going to be all for this question. Now finally, let's consider the marks awarded for this question. At the start, when you apply conservation of energy, writing down the equation like this gets you 5 marks, substituting in the two kinetic energies gets you 5 marks, and substituting the potential energy gets you another 5 marks. Now from this, when you simplify down and you get the answer given in the question, you get another 5 marks. In the next part of the question, when you figure out that the bead is going to leave the wire at theta is equal to 2 pi by 3 radians, and then you substitute and get that v squared is equal to ga over 2, you get 5 marks. And then applying s equals ut plus half at squared when you do in the horizontal direction, writing down the equation with all the substitution gets you 5 marks, simplifying to t equals root 6a over g gets you 5 marks, and then in the vertical direction, when you substitute all of the values, you get 10 marks, and then simplifying down with the substituted t gets you another 5 marks, and getting the final answer of height equals 3a over 2 gets you another 5 marks. Now finally, for this single sentence that we have here, where you say by conservation of energy, the speed of the particle is equal to root 7 GA over 2, you get 10 marks. Now additionally, you could have also said by conservation of energy, maybe something like since the particle returns to A or something like that. You could have written something like that, but in the actual marking scheme it doesn't give that much detail, which is why I just wrote this sentence. But ideally I would like some more detail like this. So anyway, that gets you 10 marks, and that is the end of this question. So I hope you enjoyed. If you have any feedback, post it in the comments down below. Thank you for watching, and goodbye.